Hello everyone, my name is Wooyoung from Han University in South Korea, and my advisor is Professor Simon Song. The topic of this talk is the transient model for erosion mission process of stratified layer caused by a turbulent impinging jet. The erosion mission phenomena of the stratified layer caused by a turbulent impinging jet is of interest when it comes to evaluate the hydrogen risk of nuclear power plants in severe accident, because it determines the some hydro behaviors of stratified hydrogen layer in a containment building and affects the safety of the building. To manage the severe accident quickly, it is important to predict the hydrogen behaviors quickly and accurately. This can be achieved only if there are many databases and simple one-D theoretical models. To obtain databases, the experts in Germany, France, Switzerland, Japan, and Korea have constructed these large-scale experimental postulates, and they have performed the erosion mission experiments. With the obtained databases, they have investigated the transient erosion mission process over a long period of time using temporal variation of density interface location, jet velocity, and jet width, which here represent the transient behaviors of stratified hydrogen layer and impinging jet flow. However, different flow behaviors due to different conditions and insufficient databases due to high cost make it difficult to characterize the process. To predict and evaluate the process quickly and accurately under various physical conditions in severe accident, transient models with the impact of the physical conditions are absolutely necessary, but they have not been developed. Of course, there is a theoretical model developed for the turbulent jet impinging on a uniformly stratified layer. The previous model shows the time average scheme of the impinging jet flows at a quasi-steady state like this. However, the previous model cannot be used to predict the transient erosion mission process because it's valid only for the quasi-steady state, as you can see. And it considers only turbulent jet impinging on a fixed density interface of a uniformly stratified layer, where the density gradient and pressure gradient do not exist. Unfortunately, real conditions are more complicated than this. The condition could be including the elapsed time and presence of density gradients inside the stratified layer and pressure gradient inside the jet due to the impinging rate. To predict and evaluate the transient erosion mission process over a long period of time, we need to develop the theoretical model of the turbulent jet impinging on a stratified layer by considering the elapsed time, the density gradient of the stratified layer, and pressure gradient jet. If we consider these conditions, the variation of density interface location, jet velocity, and jet width are expected to show nonlinear behaviors with time, unlike the previous steady model. So the main object is to develop the transient model for the characterizing the erosion mission process for stratified layer and turbulent impinging jet with both density and pressure gradients. The first, we performed erosion mission experiments, and second, we developed the transient model by considering these conditions, and finally, we validate the model using the experiment data. From now on, I'm going to explain the experimental setup. The Korea Atomic Energy Research Institute made a spark test facility for the erosion mission experiment. The spark test facility comprised from the cylindrical pressure vessel, gas sampling pipes, and jet node. We first made the stratified layer using helium gas instead of hydrogen gas, and then we injected the turbulent jet using an air at a constant flow rate through the jet nozzle. To measure the velocity field, we used the large-scale PIV system. The width or height of FOV were about 84 centimeters. A gas mixture inside a vessel was sampled through the gas sampling pipes, and each density is calculated based on the helium concentration measured by thermal conductivity sensor. We performed the experiments with different flow rates of air jet while keeping the helium concentration of a stratified layer at 34%. In this study, jet source Reynolds numbers of case 1 and case 2 were what the 10,000 and 15,000 respectively. These cases were chosen based on the scenario of the postulated severe accident. From now on, I'm going to explain the experimental results. This slide shows the temporal variation of vertical density distribution and time average axial velocity field inside the vessel for case 1. Each vertical axis is vertical position rescaled by the jet nozzle radius and jet increment coefficient. The horizontal axis are local density and the horizontal position rescaled by the jet fluid density and jet nozzle radius respectively. As shown in figure A, the interface location jet IT and the density gradient went up together as time increased in the course of the erosion mixing process. From the result, we found that the density gradient has formed linear over a wide vertical range and varied with time. Similar to this, as shown in figure B, the mean axial velocity and half width of the jet increased as time increased at a fixed vertical position. This slide shows the temporal variation of density interface location, jet mean axial velocity, and jet half width for case 1. Each horizontal axis is elapsed time rescaled by the jet increment coefficient, jet nozzle radius, and jet mean axial velocity at jet nozzle axis. The vertical axis rescaled the interface displacement, jet mean axial velocity, and jet half width. As shown in figure A and B, all the variation showed the linear behavior with time, where it went up rapidly in initial stage but slowed down afterward. On the other hand, we could not predict the linear behaviors despite use of the corresponding previous model, which do not consider density and pressure gradients, but constant only less time. From the result, we found that the nonlinear behaviors were induced by the presence of density gradient and pressure gradients, which means that the variation depends mainly on the gradients. Therefore, the gradients should be constant to predict the nonlinear behaviors in the variations. From now on, I'm going to explain the development of a Transient model for a turbulent jet impinging on a linearly stratified layer in the presence of pressure gradient. As I mentioned before, the variation are affected by density and pressure gradients. To develop the model, it's necessary to include a negative buoyant force, negative pressure force, and strength of density gradient and the strength pressure gradient like this. These differential equations of quantities are derived from the flux conservations inside control volumes. There are 5 fluxes from the volume flux to the energy flux. For the 5 distinct regions, the same derivation process has been performed. The regions are divided with the strength of impinging jet. The results, the governing equations for each region are derived. For example, this is the equations of the region 3. The equations are expressed in the dimensionless form and including the new terms, which represent the impact of the density gradient and pressure gradient. And then, the equations are calculated piecewisely for each time step. This slide shows the comparison of the quantum model with experiment data on the variation of density interface location, the mean axial velocity, and the half width. In these figures, the black and red line represent the prediction of transform to previous model and quantum model respectively. The difference between the previous model and current model are like this. From the result, we found that the current model predicts the nonlinear behaviors were unlike the previous model, even though the current model had a little difference from the experimental data at the initial stage and at the other point. This good agreement results from the consideration of density and pressure gradients. The values of the RMS error also proved the difference between the prediction of the current model and the experimental data was smaller than the previous model. This is the conclusions. We performed the experiment on the Erosion mission process of a stratified layer caused by turbulent impinging jet. The variation had non-linear behaviors with less time due to the presence of density and pressure gradients. We developed the transient models to predict the non-linear behaviors by considering the gradients. As a result, we found that the prediction of current model was in good agreement with experimental data. This is the end. Thank you for your attention.